Mr. McBrien, and this is SPH3U, Equations of Motion. Today we're going to dig a little deeper into the mathematics of kinematics and look at deriving the 5 equations of motion and look at some practical tips for how to apply these equations to solve problems. We have really kinematics can be distilled down into what amounts to 2 equations. The first is here, average speed. So if we have a starting speed, a final speed, we take an average of that. That's equal to our change in distance over change in time. Very straightforward. One of the fundamentals of what we're doing here. Now remember that this does imply constant acceleration, so we don't have a changing acceleration in this kind of a problem. And we can also extend this out to the directional case, to velocity. So the average velocity is equal to the total displacement, change in displacement over the time interval. We have a second equation. Acceleration is the change in velocity over change in time, over the time interval. And of course that can be rewritten as v2 minus v1 over delta t. No great shock. We can rearrange any of these equations as we've done in math class. Rearrange any of them to isolate for a given variable. So if we take our acceleration case, if we want to, we can isolate for v2, our final velocity. And what are we saying? We're creating an expression where if we know the acceleration, the starting velocity, and the time, we can get v2, no great shock. And how do we do this? Well, first off, we need to get delta t off the bottom, so we multiply both sides by delta t. That gives us a times delta t equals v2 minus v1. And this is still pretty intuitive, right? The acceleration times the time interval equals the change in velocity. So now to isolate for v2, it's a trivial exercise. We add v1 to both sides, and we get our final expression, v2 equals v1 plus a delta t. Easy stuff, right? Okay, but we can do this for virtually any problem, and we can keep in mind that as long as we have a constant acceleration case, both these expressions apply to any given system. And we can say that our first expression covers everything except acceleration, and our second expression covers everything except distance or displacement. When we combine the two, we can span the entire range of these parameters. In other words, we can solve for any parameter in a kinematics problem. Okay, so let's dig in and talk about an example to illustrate it. So I chose a case here where we need the displacement given the starting velocity, the acceleration, and the time. So a car is going 30 meters per second north. It brakes at 2.3 meters per second squared. After 2 seconds, what's its displacement? So we're not asking for the final speed or the final velocity. We're asking for the displacement. So how do we solve this? In fact, we could do this graphically. So this is just like the weekend homework. We could solve for the area underneath the velocity time graph, just like we did on the weekend, and we could get an appropriate expression. Now, don't get confused. In this case, our particular example, we were braking, so the slope would be negative, but all of the mathematics is the same. Or we can take, so we don't have to use graphing in order to apply those concepts, however. So we can derive the equations directly by using the two expressions, combining them, and solving for any given variable. So in our case where we want the distance traveled without knowing v2, we can eliminate v2. How do we do that? Well, we already solved for v2 in the acceleration expression right here. We can take the average velocity expression and simply substitute in v1 plus a delta t into the v2 term. And we've done it here. And then from there, it's simply manipulating the algebra. We collect together the v1 terms. Then we can propagate the 2 into the 2 terms, getting v1 plus 1/2 a delta t equals delta d over delta t. And then we can, of course, get rid of the delta t term on the right-hand side by multiplying both sides of the expression by delta t. When we're finished, we get v1 delta t plus 1/2 a delta t squared equals delta d, or we can reverse that and we get the expression that we need. Delta d equals v1 delta t plus 1/2 a delta t squared, just like we did from our geometry solution. Okay, let's look at another example. So a car is 200 meters from the intersection and it's traveling at 30 meters per second. If it accelerates at 5 meters per second squared, what's its speed when it gets to the intersection? So what's challenging about this problem? Well, the first is we're not being asked for the time when it gets to the intersection, we're being asked for its speed. And so we're going to have to get a little bit creative about how we do it. But it's no different than the other situation. We simply say the thing we don't know is time. We isolate for time and then rearrange the equation. And with a little bit of manipulation, our final speed squared, what we're trying to find, equals our starting speed squared plus 2 times the acceleration times the distance to the intersection. And from that we can quickly get our speed of the car as it enters the intersection. And essentially any of these problems could be solved that way. We just need to identify what we've been given and what we need to calculate, and then find the equation that relates those variables. Now, you're not going to be expected to isolate those variables every time. You have your formula sheet, and you just need to pull out the equation that's already been done for you from the 5 equations of motion and use the appropriate one. Okay, let's try an example in anger here. So a sled's sitting at rest and is accelerated at a rate of 2 meters per second squared for 3 seconds. How far does it travel during those 3 seconds? Again, not our typical thing. We'd be asked, in the simple acceleration problems, we'd be asked what's our final speed. We're not asked for the final speed, we're asked for the distance. So, our givens, v1 of 0, acceleration of 2 meters per second squared, and our time interval of 3 seconds. Our unknown is how far it travels. So we can go back to our formula sheet, find the appropriate formula, and it's the one that we derived earlier, of course. Delta d equals v1 delta t times 1/2 acceleration times delta t squared. Substitute in, and we get 0 for our v1 plus 1/2 2 meters per second squared times 3 seconds squared. Cancel our units and get meters, 9 meters. Okay, there's plenty more problems for you to work through over the weekend. Please start working through homework set 3, the equations of motion, and we'll meet back up next week. And please don't forget you need to bring your design for your catapult, proposed design for me to approve. Thank you and have a great weekend.